Okay, so how is everyone today? Good? All right, let's get right to business. Okay, so today's what, the 29th? And last time we were talking about anti-differentiation by parts. And as a reminder, in case it wasn't clear, the terminology that I'm going to use is antiderivative and integral. Okay, so then so antiderivative So in particular, antiderivative in all contexts, in every conceivable context, always means you're asking the question. It's like if you built a big building, that was somehow like the derivative. If you put an x squared in the front door, then out the back door, 2x would come out. And antiderivative is what do you get if you push the 2x back in, and then whatever pops out the other side. So running the derivative in reverse, that's antiderivative. So I'm going to use these terms, antiderivative and integral. So this is what I'm going to say. But do understand that the textbook mentions this. But then it sticks to a different terminology. What does the textbook refer to this one as? It calls this one indefinite integral. Indefinite integral. And what does it refer to this one as? A definite integral. And to a large extent, words are just arbitrary, and I agree with that view. But also, to a large extent, words influence the way that you think about something. So. As a result, I think using this terminology has too many downsides, so I will refuse to use it. Okay, good. To remind you, the by parts formulas that we discussed last time. So the anti-differentiation by parts formula looks like this. So you want to compute the antiderivative of u multiplied by dv. Okay, and the by parts formula is that this will be u multiplied by v, and then what?
Plus.
Okay, the other one. Minus. Right. Minus what?
V multiplied
Right, du multiplied by v, and then usually you write it like so. But I've only written what was said. Surely this is not quite right yet.
integral.
Right, anti-differentiated. Good, like so. So this is antiderivative by parts, and then notably. The right-hand side, when you evaluate it, what kind of thing will it be? Will it be like a cat or what? No. This? No. This will be a function, right? So this is a function because u and v are each functions. If the problem says x, then u and v are each functions of x, and then you're subtracting antiderivative of function of x. So the result of the right-hand side is a function of x, and plus a constant. Okay. Whereas when you evaluate an integral, what kind of thing does when you evaluate an integral, what kind of thing is it? A number, right? A number that represents this. In the end, if you draw a nice picture, the signed area of a certain shape. Okay. So there's a corresponding integral formula. So the way that we'll get it done is I'll just first copy the antiderivative formula. So far I've just, all I did was just copy the antiderivative formula. And then now I'm going to write down the modifications necessary to turn it into the corresponding integral formula. So if we want the left-hand side to be an integral, well, that's easy enough. We could just write, you know, the limits a to b. So now this thing on the left-hand side, the kind of thing it should be is that it should be a number. Okay, and then you know, when you evaluate it all out, this, you know, if I needed to write limits a to b for this thing that was formerly an antiderivative, now it's an integral. Is it clear that I surely must do the same thing for that antiderivative? Okay. So now both of the antiderivatives have been transformed to, have been modified to be integrals now. Is this formula correct as written? No. Why not?
Because you need the boundary times the a to b.
Right. So let's consider just from the point of view of just, you know, what kind of thing is each piece. So when you evaluate this thing, what do you get? What kind of thing? A number. What about when you do this one? And what kind of thing is this as written? It's a function currently. Right? So does everybody see that there's like a serious problem here? In order for this to make any sense whatsoever, this has to be a number. And the way that the way that you get that number is you perform the boundary evaluation a to b, like so. Any question about the formulas? Finally, when you're doing by parts, what you do is you look at the thing you're attempting to anti-differentiate, and you analyze all the individual factors according to a certain acronym. And we wrote it down last time. So what's that acronym? ILATE. And you know, the ILATE thing is just a heuristic. It's not like some set in stone thing, you know. And you know, there's on certain problems, sometimes, in fact, the L should come first. Okay, so you could write it like this, so like or liate, I guess. I don't know. But more or less, the A and the T and the E are pretty much in the right order. So, what does the I stand for? Inverse trig functions. L? Logarithms. A? Algebraic things. And specifically, what kind of things fit in that category? Polynomial things, radical things. Okay. T? Trig. And E? Exponential. Right? That doesn't mean has an exponent. That means an exponential thing. Like x squared has an exponent, but it's not exponential. Right? 2 to exponent x, that's exponential. All right, good. So let's have an example. So we did an example last time, and I asked you to differentiate the answer we came with and make sure that you got back to the beginning. So did it work? No one did it. I haven't even thought about that. All right, well, it works, I promise. So let's have this one. How about antiderivative of the logarithm of w dw? And I'm only using w because I don't want you to, you know, get the wrong impression that x is somehow sacred. All right. So what do you think? What do you think? Huh.
I'm still writing it down.
So here I'm going to write down a wrong answer. Okay, so if you're going to copy what I'm about to write, please carefully copy that it's not correct. So here's a minority of students in 2414 will respond in this way. They'll say it's equal to 1 over w plus a constant. Okay, so what's wrong with this? No? Right. What are we trying to do? We're trying to anti-differentiate logarithm of w, right? Okay. So the thing that you do know, and the thing that kind of looks like this, it does look like this, but this is just utterly not right. There is something that actually does look like this. It is this one. The derivative with respect to w of the logarithm of w is what? That's 1 over w. Right? And so, you know, notice that this is antiderivative. So it's like the exact opposite, you know, of this. So they're related, surely related, but you know, this would be like, you know, I ask you to take one step forward and then you take one step back. Okay, you kind of got the right idea, but wrong direction. Okay, so this is not right. Okay. Well, there's nothing that we can do to algebraically simplify this. There's no substitution that we can make. You know, we can't say u is equal to, you know, whatever. That's not going to work. So here's a hint. Let's consider it to be written in this way: 1 multiplied by logarithm of w multiplied by dw. So it's a slight hint there. Okay, and we're going to use by parts. So let's label the factors. Notably, you don't ever label the differential bit. Okay, it doesn't get a label. But you can see now that there's 2 factors. What kind of thing in the by parts acronym is a 1? It's an algebraic thing, right? Because it's well, it's a polynomial. Okay, so this one is algebraic. And what kind of thing is this one? Logarithmic, right? Okay, so in the acronym ILATE, which one comes first? The log does. As a result, that's telling us that we're going to select log. So we're going to select log. And specifically what we're doing is that because this is the formula, u dv, what the ILATE does, it tells you the selection for u. Okay, it's telling you what u is. So u is a logarithm of w. But because the ILATE thingy tells you what u is, and because everything else has to be dv, it also tells us what dv is. So what's dv? Okay, so right now this is what I heard. So I heard dv is 1, but I want to impress upon you just how incredibly incorrect this is. Okay, and I'm not picking on anyone. That's not my intent. But my intent is for you to understand that the kind of thing on the left is called a differential. In this class, usually it's called a differential. But you know, if you go on and take more math, it'll be called a differential form, and specifically, it'll be called a 1 form. It's called a 1 form, more or less, because there's this 1d thing, right? So there's a d thing there. Now on the right-hand side, how many d things are there? None. So the right-hand side is called a 0 form. So the left-hand side is a 1 form, the right-hand side is a 0 form, and if you write this, you're saying that this 1 form is equal to that 0 form, and to the grader, okay, who's a graduate student, that's approximately like saying that you know, this giraffe is equal to that velociraptor. You know, they're like, those aren't even close, right? It's not even close to the same thing. Okay, so it's not dv is 1, it's dv is what? 1 dw. So now that I've written this, how many d thingies are on the right? 1. So this is, the left-hand side is a 1 form, the right-hand side is a 1 form. So this at least makes sense. All right. So now in this formula, notice that there's 4 items. There is a u, there is a dv. Okay, and then on the right-hand side, there's u again, so I won't write it again. But here's a new thing, a v, right? That's new. And there's a v again, so I won't write it again. And then du, that's new. So there's 4 in the formula, the biparts formula. There's 4 items. What I'm telling you is that ILATE informs you how to select the first 2. And then from these first two, you're able to determine the last two. So what can you get since from this? Since we said u is log w, what can we get from u? We can get du. Okay, so then I'll write this out in the long way one time. So, you know, you could say du dw is 1 over w, like so. And then, of course, du dw, that's, you know, I hope your calculus instructor really said loudly and strongly that even though that looks like a fraction, like, you know, it looks like, you know, like 3/4, it's not a fraction, okay? Nevertheless, the way things are, you can actually treat it like a fraction, and you can solve for du and get this, 1 over w dw. Okay, and again, to make sure that you understand this, to make sure that the things that you write always make sense, how many d thingies are on the left? 1, so this is a 1 form. How many d thingies are on the right? 1, so this is a 1 form. Now, understand that the way things are counted is that, you know, concerning this line right here, how many d things are on the left? 2 of them are. And how many d things are on the right? 0. Okay, so that's a little bit curious. But that basically comes down to the thing that your calculus instructor was saying. It's not really a fraction. Okay, so specifically, in this case, the du that's in the numerator, scare quote numerator, is counted as a positive one. And the dw that's in the scare quote denominator is a negative one. So this is like, you know, giveth one, taketh one away. Okay, so the left-hand side is a 0 form, and the right is a 0 form. Good. So then what can we get from dv? We can get v. So how do you get v from dv? Antiderivative. Good. So v should be antiderivative of dv, like so, which of course is antiderivative of dw, which is what? Just a w. Now, here's the deal. If that were the only problem we were doing right there, then it would be necessary to write plus c. Like if I just you know, if you saw that exercise on a quiz, right? Wouldn't that be lovely? You know, you'd have to write w plus c. But here you don't write plus c, so there's no plus c yet. The reason is because what we're doing in the formula is we're transitioning from the left-hand side to the right-hand side of the formula. Do you observe that the right-hand side of the formula still has an antiderivative? It's still there. As a result, it's not time for the plus c yet. It's not time yet. Okay, so the right-hand side of by parts is right there, uv minus antiderivative v du. So uv logarithm w multiplied by w minus antiderivative v du, so w multiplied by 1 over w dw. Any questions so far? Okay, so now what? So we're not quite finished. Again, this is why we're not writing why we didn't write plus c yet, because there was still antiderivative to go. So how do we do this one? Yeah, we need to perform an algebraic simplification. So this would be, you know, logarithm of w, multiply w, subtract antiderivative. The w multiply 1 over w cancels, so that you get this. Okay, and then, okay, can you do the antiderivative of dw? Sure, it's w, right? So it would be logarithm of w, multiply w, subtract w plus c. But wait a second, you know. Just right there, I did antiderivative of w and got a w, and I said, no, you don't do the plus c. And then here I did exactly the same antiderivative, and now I'm saying, oh, you must have the plus c. What's the distinction? Yeah, is that when we move from here to here, there's no more antiderivative. Right? It's done. So in a sense, the plus c is like the period at the end of the sentence. Any questions? And again, for those of you that are, hopefully interested in the counting argument of forms, so notice this expression right here. So this term right here, log w multiply w, how many d things does it have? None. So this is a zero form. And then this thing that we're doing right here, antiderivative of dw. Notice it has a one d thing, one dw. But what the antiderivative actually is, what it actually does is it lowers the form number. So this is a one form, and by the time the antiderivative is done with it, the result is a zero form. So this is a zero form. Subtract another zero form. Okay, so the reason why I'm telling you this is so that you can mentally count in the same way that the grader is going to mentally count. Because what's going to happen is that if you don't write the dw stuff or dx or what have you, then you're going to get points taken off. Because the grader is a graduate student and they've had this put into them pretty seriously. Good. Let's have another example. How about antiderivative of, well, this will be fun, t squared multiplied by exponential of 3t dt. Okay, so this one is like it's almost possible to do a substitution, right? If in that exponential there, if it were not 3 multiplied t, if instead that 3 was the exponent, right? If it was t cubed, what would we be able to do? Yeah, we'd be able to do a substitution, right? Because you could say, I'm saying if instead of 3t it were t cubed, you could say u is t cubed, and then du is something something t squared, and you'd be able to go. Okay, but we can't do that. So you could run through the checklist of all the different techniques that you know, and you'll come to the conclusion that you're not able to use any of the things that you know, except for this new thing, by parts. So that means that we need to label some things. So what kind of thing is t squared? It's algebraic. What kind of thing is exponential of 3t? Exponential, right? And in the acronym, which of these comes first? A comes first. As a result, using U's and V's and things like that, what is that telling us? U is t squared. Okay, so then U is t squared. And then what is dv? Very good. So dv is always everything else. Okay. So then what can we obtain from u? Du. So du would be 2t dt, like so. What can we obtain from dv? V, by anti-differentiating. So this would be exponential of 3t, and then all of that over 3, like so. The thing that I use there is that the antiderivative of exponential of u du, just like that. That's the loveliest one that there is. That's just exponential of u plus a constant. And then if you write antiderivative of exponential of, now I'll put a constant in front of that u, so that's k u du. Well, you could do a substitution. You could say v is ku and work it all out. At any rate, you'll end up getting this exponential of k u divided by k plus a constant. So essentially that 3, ends up being a division by 3. Good. Again, no plus c there. I'm sorry? No, right? Because because what I did is I anti-differentiated dv, right? So again, with the counting argument, if you anti-differentiate this, so just that thing that's above my fingers there, exponential 3t dt, that's a 1 form. If you anti-differentiate it, that lowers it by 1, and it becomes a 0 form, like so. Good. So the right-hand side of my parts looks like this. It's uv minus antiderivative v du. So that'd be t squared, that's u, and then v is that, exponential 3t over 3. So uv minus antiderivative v du, like so. Okay, any question getting to here? So that's uv minus antiderivative v du. So now I'm going to simplify this a little bit before I ask for any more input. So t squared multiplied by exponential 3t divided by 3. I'll factor out the constants and write subtract. No, I'll leave them in, but I'll collect them together. That'll make it work nice. Subtract antiderivative 2/3 t multiply exponential 3t dt. All right. Now what? Well, you know, can we perform some kind of algebraic simplification? Nah. How about can we do a substitution? Nah, that's not going to work. In fact, you can go all the way down the checklist and find that none of that stuff that you knew last week works. So, oh yeah, I guess we could do by parts. Okay. So let's. I'll label this thing. What kind of thing is that? It's algebraic. What kind of thing is this? Exponential. Okay, now, so to clear up some thoughts here, is that are we really doing an exercise where by parts is required twice? Yes, we really are. Furthermore, because I've shown you an example where you need to do it twice, understand that that means that in principle I could give you one where you need to do it arbitrarily many times. Right? But you know, that has to be bounded by like reasonableness, okay? Because after all, we're asking some poor graduate student to grade it, right? So like, can you imagine doing a by parts exercise that requires you to use it 10 times? And how awful it will be for you to do it? Now understand that there's 600 of you, and so, you know, there's just 50 of you in here, but you know, generally there's 600 of you. Some graduate students got to deal with that. So as a result, it never really goes beyond 2. Okay. So that's telling us what are we going to select for u? The algebraic part, right? Now, because we already used u, instead of writing u, I'm going to write a u but with a party hat on it. Okay? Just so it's clear, you know. So I'm just going to put like a little hat on it, a little wiggle hat, because you know, in math you need to not reuse names. That's a bad idea. You know, there's a person in real life named George Foreman. Yeah. He's like real super famous, you know, boxer, and he makes like sandwiches and stuff these days. Yeah. But he's got like 13 children, and like 8 of them are named George. And that's I don't believe I'm exaggerating. I think that's pretty close to the truth. But at any rate, that would be confusing. To you know, to live in that house. Can you imagine?
I think they all have like different nicknames, because I was looking him up one day, and it was like each one had a different nickname. I'm like, that doesn't help.
Georgia, Georgetta, you know, all this. Okay. So, fine. You know, instead of calling it George, I'm calling it Georgia, you know, with the hat. Okay. So 2/3 t, and then dv party hat should be what then? Everything else. So exponential 3t dt. All right. So then from u, party, we can find du party is 2/3 dt. And from v party, we can find v party hat is equal to what? Exponential of 3t, and then what? Divide by 3. And even still, we don't have a plus c, because again, we're using the right-hand side of by parts, okay, to make it right. Okay, so the right-hand side of by parts is uv minus v du. So I'm going to write that down. So uv, so u v minus antiderivative v du. Okay, and now I want you to imagine that I've stopped. That this is all I'm going to write. Okay, so for this line, I mean, do I have it correct then? So I'm gonna keep going, but I'm saying that there's something wrong with this line here. Right? Somehow I wrote uv minus antiderivative v du, but nevertheless something's not right. Okay, so now I'm going to simplify this. This 3 can come over and be with that 3, so that this would be 2/9 t, and then multiply by exponential of 3t, and then subtract. This is 2/9, so that can factor out. And then what's the antiderivative of exponential of 3t? Right, even yet again. So this would be 2 over 27, because we've got 3 3's down there now, times exponential of 3t, and then plus a constant. Okay, so the 2, that 2 is that 2. 27 is 3, 3, 3, right? 3 multiplied by 3 multiplied by 3. 2 of the 3's are these, and then one more came from that antiderivative. Nevertheless, this is not right. What's not right about this? Right. Because remember, what we were doing is that, we got here and then we looked at this one and said, oh yeah, I love this by parts thing, let's do it again, right? But before we did that, the second time, we already did this. Okay, so the reason why I bring this up is that on these kinds of exercises, a very common error that I find students make is that many students get to here, and this is what they've written, but somehow, like this just, your eyes got off of it, and then never came back to it. Right, so I just like left that out. Furthermore, notice that's a so I'm going to fix something. So, okay, now I'll write this term. So it was forgotten, but now remembered. Nevertheless, it's still not correct. I'm sorry? No, we only need one constant. Right, so look, this is saying that thing subtract that antiderivative. Does it say just subtract like the first part of the antiderivative and then do whatever you want with the rest of it? No, right? It says subtract all of that. So what I'm saying is that, you can imagine that there's some implied green parentheses right there, right? Subtract all of that business. So that means that really this should, these green parentheses are here, like so. And do you observe that now that subtraction distributes, and what comes of that? Now that's a plus, right? So specifically, this to here, this should be a plus. Now it's right. So I'm just, trying to help you navigate the minefield of this kind of thing. Now that being said, because this is t squared, essentially, we had t squared multiplied by exponential. That means we had to do it. We had to do integration by parts twice. Okay, if it was t cubed, we'd have to do it 3 times. If it was t to 2414, you'd have to do it 2,414 times. Okay, now, there's something in the book that we're not going to go over, but it's maybe of interest to you, that tells you how to evaluate expressions that look like this, where this is a polynomial of big degree, you know, 10, 20, or what have you. And you can look it up. It's called the tabular method. But it only works, it's sort of really, really specialized. So it's how to do antiderivatives that look like this. So x to n multiplied by exponential of x dx, where n is in the naturals. Okay, I just want to let you know that it exists, and you know, you could have a look at it. And we could have, if we had known that, we could have done this exercise in, you know, like 30 seconds. Good. So last of these before we go to the next thing, how about the integral from 0 to, oh, let's back up. I've got to say something. About the inverse trig functions. All right. So, you know, you got the trig functions like sine and cosine and what have you. And if you want to undo, you know, if you want to do the inverse of the trig functions, then, you know, the inverse sine, you know, its name is arcsine. Okay? So, the book, you know, if it writes sine of theta, like so sine theta, then what the book usually writes for the inverse is it will write something like this. So sine, and then it'll put a superscript -1 right there, and then write, you know, whatever variable that the exercise is about, like right there, sine superscript -1 of x. All right, that's okay, I suppose, but the way I'm going to write it instead is I'm going to just write arcsine of x, like that. Now, the reason why I'm going to write arcsine in the end comes down to this, is that if you want to take sine, of theta and then multiply it by another sine of theta, so it's like sine of theta and then another sine of theta, and then you want to multiply them together, then the way that let me write it like this. So sine of theta, and then multiply it by another sine of theta. So if we had like two x's multiplied by each other, x multiplied by x, you know, you'd write that as x squared. Okay? So the way the book wants to write that is like this. They put sine, and then they put a 2 there, and then they write the theta. I think that is reprehensible. I wish the author were here so I could ask them to leave. Okay? So, but this is terrible, terrible, terrible. And the reason is because if that exponent, if this exponent here means square, then surely that one should mean reciprocal. It does not. Okay? That's why I'm going to write arcsine. And I'm never, ever, except for this explanation, going to write this either. Rather, I'm going to write it like this. Sine of theta squared. Okay? The reason is because if you just take the trig functions out and you just ask, you know, what should, you know, if you want to write x multiplied by x, then how would you interpret x to -1? 1 over x, right? The reciprocal of x? Yet, that's not what this means. You know, if this means this, then this surely means this. So as a result, I'm going to not do that at all, and I'm going to write that. Okay, good. Now that I've got can get off the soapbox there, I can ask the question, how about integral 0 to 1 of what? Arctangent of theta. Why not? Arctangent of theta d theta. Theta doesn't make any sense, but in the usual sense, right? Because what kind of thing is the input to, well, you put angles into tangent, right? And it gives you a ratio. So arctangent, you give it a ratio, and out comes an angle. And then in our heads, you kind of associate theta to be an angle. So strictly speaking, like according to that convention, this doesn't make any sense. But to understand that there's nothing, to a certain extent, there's nothing to a name. All right. So how do we do it? In the first place, this is an integral now, not an antiderivative. Okay, what formula? Okay, we're going to need to do by parts, right? Because the thing that you need to know is that the derivative with respect to theta of arctangent of theta is what? Okay, almost. 1 over 1 plus theta squared. Okay, good. So that's something you need to know in order to proceed. All right. So how will we use? So we're going to need to use by parts. How will we do it? Well, remember that with by parts, you label all of the non-differential factors. So like there's two factors here, the arctan thingy and the differential thingy. So at the present time, there's just one factor. You see what I mean? Like, can you see that there's kind of a question? So what did we do in the case of logarithm when, we considered it to just be 1, right? So again, you could think of it like that. You could say, okay, integral 0 to 1, and then I'll write the implied 1 there, arc tangent of theta d theta. This 1 is an algebraic thing. This arctangent is what kind of thing? No?
Inverse trig.
It's an inverse trig, right? So it's an I in the I-late thingy. So that tells us what we're going to select for u. So what are we going to select for u? Arctan. So u is arc tangent of theta, and therefore dv is what?
1 theta.
Very good. Always everything else. Okay, so then from u we can find du. So what's du then? Well, it's that, what I wrote over there. So 1 over 1 plus theta squared d theta. And then antiderivative of v would be just theta. Any questions so far? All right. Then the right-hand side of by parts is uv minus antiderivative v du, except now it's going to be integral. So uv, arc tangent of theta, u v, minus v du. Okay, now how do I need to edit what I've written here to make it right? Right, for this one, it has to be boundary evaluated. 0 to 1. And then what else? Still yet one more edit needs to be made. Yeah, this needs to still be integral 0 to 1. Good? Okay, so concerning this, so we'll need to evaluate arctangent of 1, and then multiply by 1, and then subtract arctangent of 0, and then multiply by 0, and then subtract integral 0 to 1, and I'll write it as theta over 1 plus theta squared d theta. Okay, so then, yes? I don't follow your question.
The 0 and 1 for the bar in the red.
Yeah?
Yeah. Why aren't those substituted? Are you Arctangent for them? 2 lines above the screen? Yeah.
You mean why am I not changing the limits? Well, because I'm not changing the variable. No, I understand now, I think. So when you do substitution, like a switch from, say, variable x to variable u, you change the limits, right? But the changing of the limits happens when you change the variable. So notice that here, what's the variable name? Theta. And then here, what's the variable name? Still theta. As a result, you don't change the limits. Other questions? All right, so then, you know, arctangent of 0, whatever that is, who knows, right? You need to multiply it by 0. Now, what's the arctangent of 1? This is something you should know off the top of your head. Pi over 4, right? The reason why it's pi over 4 is because, remember that tangent, you know, SOHCAHTOA or whatever, opposite over adjacent, tangent of an angle is a ratio. And if the ratio of the angle is 1, that means that the rise and the run are the same. So now, what's the slope of the line? What's the angle of the line where the rise and the run are the same? Pi over 4, right? So this is pi over 4 times 1. So altogether, that stuff in there is just pi over 4. Okay, then subtract. Now, how do we do this? Actually, you might be able to do by parts, I'm not sure, but there's a better way to go. You could do by parts, you could, but what I'm saying is that there's a better game in town than that. A U substitution, right? A U substitution because notice that if you say U, and I won't use U because I used a thing there, so then if you say W, say, is 1 plus theta squared, then what's dW? Theta, right, 2 theta d theta. So we need to do a substitution. So the substitution I'll make is that right here I'll say that W is 1 plus theta squared. If W is 1 plus theta squared, then dW is 2 theta d theta. Now we don't quite have 2 theta d theta. We just have 1 theta d theta. So I'll divide by 2 and get dW over 2 is theta d theta. And now, because I'm changing the variables here, I'll change the limits, which is to say that when theta is 0, what is W? It's 1. And when theta is 1, what is W? 2. So then now, making that substitution, this would be integral with new limits 1 to 2. Okay, then this would be 1 over W dW over 2. Any question about getting there? This is okay? I'm getting squunchy faces. This is okay? So that's because theta d theta became dW over 2, and then that became a W. All right. So then besides the division by 2, which can be factored out, we're asking, you know, the corresponding antiderivative is 1 over W dW. What is the antiderivative of 1 over W dW? Log of? Not W. Log of? Well, it could be, but even still, not enough. So log of what? What's the antiderivative of 1 over W dW? Ah, come now. The antiderivative of 1 over W dW is what? So the most common wrong answer is that, that this is the logarithm of W plus a constant. But that's not right. Absolute value. It's not, cannot be omitted, right? Good. So then now, finishing this, this would be pi over 4. and then subtract half logarithm absolute w from 1 to 2. And then, if you know, on this specific exercise, if you had forgotten the w, you know, you would have like lucked into the right answer anyhow. It still would have worked because the things that you're plugging in are both positive. So to finish, this would be pi over 4, and then subtract half, and then multiply by logarithm of 2 minus logarithm of 1. But what's the logarithm of 1? It's 0. So this would be pi over 4, and then subtract log 2 over 2. Okay, I guess that's all the time we have for today. Any questions? Okay, very good. Have a wonderful Wednesday.